Let's go ahead and get started. Last time we had class, we finished with the connection between the angle between two vectors and the dot product of those two vectors. And we discussed how when you dot something with itself, it's the magnitude squared. Worked out this formula, then tied it into this triangle with the law of cosines. And together we canceled out and decided that the dot product is the product of the magnitudes times the cosine of the angle between them. And solved for cosine of the angle between them, we get that dot product divided by the product of the magnitudes will give you the cosine of the angle. And remember, the angle is something between 0 and pi. So let's go ahead and just do a quick calculation of that for two vectors. I have a vector 3, 1, 2, 3, negative 1, 2, sorry, and a vector negative 4, 0, 2. Let's find the angle. It won't be something recognizable as far as the ease of us to be able to find the cosine inverse of it, but at least we can represent it as the cosine inverse of some number. And so that formula is pretty simplistic. It has the dot product and then the magnitude, so that's all we need. Dot product between those two vectors would be what? Negative 10? Or negative 8, sorry. So we get negative 12, and we add on 4. Yeah, negative 8. The magnitude of the vector u, we squared the 3, we squared the negative 1, we squared the 2. That's 14, and we just the root of that. The magnitude of the vector v, we squared the negative 4, we squared the 2, and we get 20. So we multiply these two magnitudes. That's our denominator. We take the negative 8, the dot product. That's our numerator, and the angle is that should be the cosine of the angle between our vectors. If we want to, we can simplify root 20 at least. We call that 2 root 5. So it's a simple calculation. Not that bad at all. Not that we're supposed to recognize what angle this is, but we can at least call it the cosine inverse of that. And of course, we can get more simplified by saying that we're not allowed to have the square root of a number that's not a perfect square. We're not allowed to have an irrational number in the denominator. And so we can go further with this and multiply top and bottom by root 70 and get something like negative 4 root 70 over 70. It doesn't matter though. You can take that first version. I'd accept that. I'm not sure. Yeah, I think my math lab should accept that too. And then cancel the 4 and the 70 and call it 2 and 35. So just represent your answer for theta as the cosine inverse of that. Either version, the negative 8 over 2 root 70, or this rationalized version, negative 2 root 70 over 35. And just so you know that's some angle. The fact that it's negative tells us something though. What do we know about the angle since its cosine is negative? It should be in the second quadrant, right? If you're in the first quadrant, between 0 and pi over 2, sine and cosine are both positive. But when you move to the second quadrant, the answer has to be between 0 and pi. And so because you're negative for cosine, it must be in the second quadrant. That's what all we can say, at least, without some certainty. We can at least say that it's some obtuse angle. More than 90. Okay? And at this point, we have to go to a calculator to get some kind of version of what it would be degree-wise or radian-wise. So it's a simple calculation, and it's the connection between theta, the angle between the vectors, and the dot product. This skill here of being able to find a vector that points in the same direction but has a prescribed magnitude, that's what we're going to need later. And so we saw how to find a vector that points in the same direction, has a magnitude of 1. Remember how we did that? We just said, well, just find the magnitude of that vector and multiply by the reciprocal of it. Divide each component by that magnitude, and you'll be guaranteed that your vector will have length 1. So that's kind of what we're going to do. We're going to make it have length 1, and then scale it out to have length 10, essentially. That's the idea. So its magnitude is 25 and 9 and 16. So 25 and 25. So root 50 is the magnitude of that vector. And we'll call that 5 root 2. So first we'll take it and scale it down, make it a unit vector, divide each component by 5 root 2. So now it has length 1, and then how do we change the vector of length 1 and make it have length 10? We just scale it by 10. We multiply by 10. And so we'll have 50 over 5 root 2, and negative 30 over 5 root 2, and 40 over 5 root 2. And we'll be guaranteed it points in the same direction as V, and it will be guaranteed that it has a magnitude of 10. You can go check it if you want. Okay. And we can reduce, we can call it, and we can rationalize too. I guess we can reduce and rationalize all together. And it would look like this: 5 root 2, negative 3 root 2, and 4 root 2. Okay. We don't have to do that in 2 separate steps. We could put that together in 1 step. Why should we have to first divide by the magnitude and then later multiply by 10? Why can't we just say that if we want the vector to have magnitude 10, then we multiply by 10 over the magnitude of the vector, okay, which is 10 over 5 root 2, which is root 2. And you see that's the change in the vector. Now it has root 2s every place. And so we can do it in one fell swoop then, and this is going to come into play later when we try to find the projection of the vector onto another vector. This idea that I have a vector which points in the same direction and which has a prescribed magnitude k, then I accomplish that by scaling my vector by k over mag v, whatever the vector is. Okay? Do it in 1 step, not 2. Okay? Questions about this slide? Sorry, I went kind of fast. Is that okay? Okay, so I'm going to tell you where the formula for, I'm going to tell you how to project one vector onto another vector and tell you where the formulas come from. You don't have to, like a lot of things we do in this class will be deriving, just like we're kind of trying to understand where the formulas came from, like with the cosine theta connecting to the dot product. Not that you have to know that derivation, but I just feel bad just throwing the formula at you. And so instead of that, I want you to know where the formulas come from. Remember that formula that we had for the angle theta between the vectors and the dot product? We had to solve for cosine theta, but the step before that, it was solve for the dot product. And so we can use that to say some things about the angle between the vectors. You see, if u and v aren't zero vectors, their magnitude is more than 0, then we can be sure that whatever sign the cosine theta has should be the sign that the dot product has. Right? We know this is guaranteed to be positive, greater than 0. If u and v aren't 0, their magnitudes aren't 0. So on my right-hand side here, I know these guys are both positive. And so when it comes time to decide the sign, it must be true that whatever sign this is the sign that the cosine theta has. And so we're going to say that officially, that u dot v and cosine theta has to have the same sign. And we just saw earlier that when the cosine of theta was negative, it came from the dot product being negative, and that was an obtuse angle. When cosine theta is positive, we're going to have an acute angle. And so we can know whether the angle is acute, obtuse, or right, just based on the dot product. If your dot product is positive, you're guaranteed it's an acute angle. If your dot product is negative, you're guaranteed it's an obtuse angle. And here's the main thing. If your dot product is 0, you're guaranteed that it's a right angle. Okay? And we'll be interested in vectors meeting at right angles. Okay? Instead of saying what we used to say for lines meeting at right angles, we said the lines are perpendicular. We won't say vectors are perpendicular. We'll say vectors are orthogonal. Okay? And so these vectors are orthogonal if the dot product is 0. So it's a simple calculation, doing the dot product, and the fact that it's equal to 0 tells you that the vectors meet in a right angle. They are orthogonal. Okay? So take the word perpendicular out and put in orthogonal. Perpendicular is going to go for lines. Orthogonal is going to go for vectors. Okay? So if anyone ever asks you about vectors meeting at a right angle, about vectors being orthogonal, you translate it in your mind to be the dot product is 0. Okay. We guarantee there'll be a 90-degree angle, a pi over 2 angle between the vectors. Okay? Okay, great. So now let's talk about one last thing before we jump to the projection. The vectors I, j, and k, they're all orthogonal, right? Their dot product is 0. Remember what I is. I is 1 along x and 0 for y, for I and j, for j and k, in the y and z direction, and j and k. These are our standard vectors here with 1 in one component, 0 in the others. They're orthogonal. They form the basis for our 3 space. And then here's a generic vector out in space called v. And this is necessary in some applications. It's not a big deal. But the angle that v makes with each of the coordinate axes, or instead of saying an angle between a vector and an axis, we'll say an angle between a vector and the I, j, and k. The angle that it makes between I, j, and k and itself, that angle between I and the vector is called alpha. The angle between j and the vector is called beta in this picture. And the angle between k and the vector v is called gamma. That's the Greek letter gamma, the third one there. And we can find out what these angles are. Okay? They're called the direction angles. They can define the vector for you. Some people, in some applications, in some graphic applications, they use these angles to define the vector instead of, the way we've been doing it earlier. And so alpha is the angle between v and I, and beta is the angle between v and j, and gamma is the angle between v and k. How can we find them? Think about what v is, generically some vector that has 3 components, v1, v2, and v3. And think about what I, j, and k are. I is 1, 0, 0, and j is 0, 1, 0, and k is 0, 0, 1. Okay. Now remember the formula for how you find the angle between 2 vectors. Take the dot product and you divide by the magnitudes. Each of these guys have a magnitude of 1. Each of these I, j, and k have a magnitude of 1. They're unit vectors. They're standard unit vectors. So I, j, and k have a magnitude of 1. So let's plug into the formula to find the angle between v and I. Let's go find alpha. Alpha then, if we do a dot product, right, between v and I, the numerator there, it will be zeroed out for the j and the k component. And what we get is simply the I component, v1. In the denominator here, we're supposed to divide by mag u and mag v, but the mag of I is 1. And so this ends up being just this number here. Take whatever your I component is and divide by the magnitude, and that'll be the cosine of alpha. Take whatever your j component is, divided by the magnitude, that'll be your cosine of beta. Take whatever your k component is, divided by the magnitude, that'll be the cosine of gamma. Okay, so you can find alpha, beta, and gamma, and in some instances they matter. In some places we care about those angles. And so if you think about it though, these 3 things end up as the components of the unit vector that points in the same direction as v. And so just take those guys and inverse cosine them to find those angles. So if you're asked for the direction or the direction angles of a vector, this is what they're talking about. Okay, questions on that? Okay, great. Yeah, I didn't write the rest of this, but of course the magnitude of j is 1, and the magnitude of k is also 1. So when you plug it into here, you'll get a 1, and that's how we're getting that. The dot product is going to be just each component because I'll be zeroing out the other components and multiplying the one component by 1. All right, great. With that said, then we need to talk about projecting a vector onto another vector. Very useful application. I want to take this vector u and project it onto v. Think about shining a light at a certain angle where I'll have a shadow of u in the direction of v. And I'm interested in that shadow. Okay? The vector projection of u onto v. That red vector there. It would be necessary for me to be able to find that vector in many applications. And so I'm going to show you, instead of giving you the formula, I'm going to show you how we can figure out what the formula should be. Okay, using a right triangle, we think about it as, if this is going to be theta, the angle between these two vectors, theta, then the symbol that I use to call this vector projection, I use the letters P-R-O-J. Now, the order in which this U and V is important. I'm projecting U onto V. So what I'm projecting onto gets the subscript position, and what I'm projecting goes on the same level as the letters P-R-O-J. This is reminiscent of like a log statement. The subscript is what you're projecting onto. So this is read as the projection of U onto V. That's that symbol, if you ever see that again. Okay. The proj of U onto V. Projection of U onto V, that vector there. Okay? The question is, well, how long is it? What's the magnitude of it? And so we can think about the triangle that's made by these vectors. It's a right triangle, right? This is a right triangle, and this is my opposite side, and this is my adjacent side. So the cosine of theta is equal to the adjacent side over the hypotenuse, which is the magnitude of U. If I want to know how long the adjacent side is, I just multiply by magnitude U. So that's how long that vector is. That's the magnitude of that vector. This number, which represents the magnitude of this vector, it gets its own name. Okay? So there's a vector projection, and then there's a scalar projection. The scalar projection is how long that vector is. It's the magnitude of your projection vector. In some books, they call it the component of U along V. The component of U in the direction of V. There's a component in the direction of V, and there's a component perpendicular to V. There's two components. Any vector can be broken into two components. One that points in a direction of a vector, and one that points orthogonal to that vector. Okay? So this symbol here is the magnitude of the projection vector. And we're going to say it is equal to this symbol here. The number, this is a number, that's how long this is how long that vector is. And so it's unfortunate that we have the scalar projection, vector projection, and this is the connection between these guys. Okay, we're going to come up with a better formula than this. I mean, who's going to know what theta really is? So, I mean, when you're given vectors, you're going to be given the I, J, and K version of them, and you might not be able to find the theta between them. And so we're going to come up with a better formula than this to find this magnitude. We need something better than this. It's not good enough. Okay, I'm sorry. So we start with this and we try to come up with something better. Remember our formula for cosine theta? It's the dot product divided by the product of the magnitudes. Why can't we just replace that? Okay. And when we do that, when we replace it, we have the magnitude of U, and then this dot product, and then here's magnitude of U down here. These guys are going to cancel each other out. So here's a nice formula which will be simple to calculate. If I want to know how long the projection vector is, all I need to do is take a dot product and divide by the length of the vector I'm projecting onto. Oops. Sorry. I just want to show you how the cancellation happens. For some reason it's not in there at all. Let me write it here. Mag U, U dot V, mag U, mag V, cancel, U dot V, mag V. Okay, that's how long it is. And then we're going to use our idea from last slide. I want the vector now. I want the vector. I want the projection vector. I want a formula for the projection vector. I know how long it is, and I know the direction in which it points. That's all you need to get a vector now. Those are the two things that define the vector. How its magnitude and its direction. And so this is the magnitude, And v is the direction. So to get the projection vector, I do the following. It has to point in the direction of v and have this magnitude. Remember what we said last time? Then to get this, this is supposed to be the guy. This is like our number 10 on the last slide. This is the k. This is the constant that tells us how long we want it to be. And then I have this vector v, and we said, well, just take your k, divide by mag v, and then put that in the direction of v. That'll be your vector. So I already have k here, u dot v over mag v, and now I'm supposed to divide it by mag v. What does that become? It becomes u dot v over mag v squared. Right? This is my multiplier. This is what I'm going to scale v by. Scale v by this amount. But the magnitude of a vector is really the vector dotted with itself. I love doing dot products, and so if I can just make it all dot products, then that's what I would want to do. So here's how you're going to find the vector. That's called the projection vector. This is your multiplier. You're going to scale v by this simple number. V dotted with itself in the denominator, v dotted with u in the numerator. And that's what you scale v by. Okay? I don't have it typed up in that kind of a way, but that's the idea though. You need to scale v by this amount. It's a number. This guy's a number here, right? A dot product is a number. So you have two numbers here, numerator, denominator, and that's what you multiply v by. So let me erase my chicken scratch again and give you the and we'll go with this version of it here. So instead of me just throwing this formula at you, we developed it. We saw where it came from. These two formulas are going to be the ones we're going to put on our cheat sheet. If someone asks you for these guys, remember the order matters, and you'll just go and calculate from those formulas. But now you know where those formulas come from. Combination of last slide and this slide, and then the connection with the angle and the dot product. Questions on that? Yes?
Can you just explain what a vector projection is one more time?
It's like I like to think about it physically. It's like a shadow. Right? You shine a light at the right kind of an angle. It's the shadow of the vector on the other vector.
So it has the same magnitude.
No, it doesn't.
Oh, it doesn't.
The magnitude of u is different than the magnitude of the project. The magnitude of the blue is different than the magnitude of the red. It doesn't have the same magnitude. This is its magnitude. This guy is its magnitude. It doesn't have the same length. If I was to have the same length, then that would like put me here. You're not necessarily going to have the same length. It's going to be the perpendicular drop down onto the other vector, essentially. Any vector that you have, you can do that too. You give me two vectors, I can project one to have the same direction as the other, and then I can also, we don't talk about it, but this is another guy we could talk about. This guy here being the perpendicular to your, or the orthogonal vector to your vector v.
So it's like it's just component, like it's like.
Yeah, that's what you used to do in physics when you do the component. But doesn't necessarily have to be in the x direction. It's in the v, it's in the generic v vector direction.
Right.
And this is used for work. I have this force. I'm trying to pull this object along this direction, and I have this. We'll find out that we'll use this for work to calculate the work done in moving an object in a certain straight line direction. Question? Yes. Hi.
So I understand how it's like u dot v over v dot v.
Yeah.
Where did the second v come from?
This v right here.
Yeah.
We have to have a vector, right? If I just do u dot v over v dot v, I just have a number. That number is our multiplier. It's what we scale v by. This guy's a vector, and this guy's a number.
Okay. But the vector that you're looking at in this case, isn't it u?
This red vector is what I'm talking about.
Okay.
Not you, the projection vector, the red one, called proj uv, I call it.
Okay.
Good question. Yes?
So in this case, with the two things dotted, like being multiplied by v, would that be like less
with the two things dotted,
Like in the last formula,
yeah.
would u dotted with v over v dotted with v, would that be less than 1?
Is there any way that that could be more than 1? U dot v over v dot v. Is there any way that could be more than 1? Is there any way to project this vector onto the other vector and get something that's longer than v? That's the rephrasing of your question.
Right, so it's not longer.
What if u is longer than v? I'm going to draw it. Here's v, and here's u. If I project that u onto that v, I'm going to be longer than v. The shadow of u on v, it'll be longer than v. That number better be more than 1 then. Good question. Yes?
Can you explain the relationship between the two circle formulas?
The relationship, this is a vector which represents this red vector or orange. I don't know, we're sure what color it is. And this other guy here is the magnitude of that vector. That's how long that vector is. This guy here is just you can use that if you want, but I just prefer to do all dot products. More questions, please. You gotta ask. Yes?
If that's the magnitude, then
Yeah.
why? I guess I'm just confused of why that's also the u dot v over v dot v. Is that also considered the magnitude?
That's a number. It's just a number. U dot v over v dot v is a number. It's our multiplier. You know, on our last slide, that number was 10 over mag v. It's a number. It's just a number that on our example, it was 10 over 5 root 2. It's just a number. Okay? It's a number that you scale v by. You're either going to scale it up or scale it down. In this case, this picture here, we're scaling v down by exactly that factor to get this new vector. It's not the magnitude of that new vector. This guy here is the magnitude of this new vector. What this guy here is a multiplier. On our last example, this was the multiplier, and it was how we scale our vector. It could be more, it could be less, as far as the length. In this case here, let me change colors just to show you the more. Here would be the projection of u onto v for this picture. Projection, of u onto v would be there. It's longer than v in this case, and then in this case it's shorter than v. It all depends on how long u is. Okay. We should do it for an example. But yeah, I'll give you a vector u and I give you a vector v, and it's just a matter of calculating. Okay? Just a matter of calculating. All right, I think the next slide is not an example of this, but no reason why we can't just come up with 2 random vectors and do it. But yeah, it's just a calculation, it's just a number, right? We're just doing dot products. Okay. The next slide is actually an application. It's that work application that I started to talk about. Okay. So you'll have examples in your homework, I think at least on the online, where you have to go calculate these formulas. And so my job was trying to tell you where the formulas came from. Hopefully I did okay with that. If not, then you can just ask me off hours. I can try to explain it again. Otherwise, if you just want to know how to, you just want to know what they are and then go and use them, then you have them now. Okay. In this case, we have some restrictions. Our force, it has to be a constant, and the object that we're moving has to be linear. We're moving it in a linear manner. When we want to calculate the work done by a force in moving an object a certain distance d in the same direction as the force, then it would be the magnitude of the force times the distance. That would be what work is. Okay, but then that's just too standard. In more instances, what will happen is we'll apply a force at an angle theta, and then the motion won't be straight line motion. The motion will be linear, but it won't be in the same direction as your force vector F. Here's the picture. I apply the force. The main picture is like you're pulling a wagon. There's some lever. You pull a wagon, you give it some force, and the wagon doesn't go up and you know, move in the direction that you're pulling it. It moves along some either a heel or a straight line. In this case, it's moving along something parallel to the floor, and that theta that you apply the force at plays a role. The distance that the object moves, so it starts here where this shaded guy is, it ends up here. This distance d that the object moved ends up being something that we can calculate with dot product of vectors. Okay, how long is that? It's this distance here, magnitude f times cosine theta, then times the d. So all it is take this same idea here, and now this is taking the place of it. And then what we're going to do instead of that, though, is that looks awfully familiar. I have one magnitude, I have another magnitude, and I have the cosine of the angle between them. So why do it like that? I mean, I might not always know exactly how to find the angle, so I'll do it as a dot product. The work will be the dot product between the force vector and the displacement vector. You have to make d into a vector, a displacement vector. Give it I and j, or maybe even k notation, and do a dot product between your force and your displacement vector. Okay? You'll be given a force vector. Maybe you'll just be given the force and the angle, and then you can put it all together using either of these formulas. Okay? If you can do it this way, that's great, because the dot product is easier to calculate. And if you do it this way, that works too. Toy wagon pulled by exerting a force of 25 pounds on a handle. That handle makes a 20-degree angle with the horizontal. Find the work done when you're pulling the wagon 50 feet. So really, I don't know why we can't just go with this formula. We have the force, we have the displacement, we have the cosine, we have the angle, which is 20 degrees. You can find the cosine of it, but I'm just going to show you how to set it up as a dot product. Our force vector, we have to break it down to its I and j components. We have to project it in the direction of the displacement. We have to project it down in the direction of d, and we find that by doing the cosine of the angle times the magnitude of the vector, like we did earlier with the traffic light question. And then the sine of the angle times the magnitude of the vector would be this. Okay, but because our displacement isn't at any angle with the horizontal, then when it comes time to set up the d vector, its j component is just 0. And so if we're going to set it up as vectors, you don't have to though, but if we're going to set it up as vectors, here are the two vectors, and we do a dot product, and we get exactly what we would have gotten from that formula with them not written as vectors, thinking about it like that. And so we multiply the force times the cosine of the angle times the displacement. And whatever number that is, that's how much work is required to move that object that distance. Okay. And the units would be foot-pounds, because the force is in pounds and the distance is in feet, so foot-pounds. And that's not normally what we like to have work in, and the units of work are either newtons or joules, and I just converted it to joules for you. But you don't have to do that with a calculator. That's definitely something with a calculator, because this 20 degrees is something that we don't know the cosine of. If you encounter a question on My Math Lab that has a strange angle, don't be afraid. Go ahead and use a calculator. You'll see that on your first assignment or second one. It's okay. But on the exam, I'll make sure that it's an angle that you should know the sine or cosine of. Okay? All right, so that's officially it for the 12.3 dot product notes. Let's go right ahead on to the 12.4 cross product notes. Okay, we'll do the same thing. We'll talk about where it comes from. We'll talk about how to calculate it. We'll talk about some properties of it. And then we'll do an application of it. This is a different animal than the dot product. Okay, the cross product of two vectors is a vector itself. The dot product between two vectors is a number, but the cross product between two vectors is a vector. And it's a special vector. It is a vector that is orthogonal to both of the original vectors. Okay? So I have a vector u and I have a vector v, and they lie in some plane. They actually define some plane. When I cross those vectors, I'll get a vector that is orthogonal to both of them at the same time. Okay? It's different than the dot product, because the dot product yields a number. And there's this formula that you're not to memorize. Okay? We had the formula for dot product, which was easy to do. This is not easy to memorize. There's so many different, combinations here that you could easily make a mistake. And so I'm going to show you a technique to calculate the cross product, but it relies on you knowing something about matrices and the determinant of a matrix. And so we'll take a detour for a second and talk about not what a matrix is, or not linear algebra or anything like that. Just how to calculate the determinant of a matrix. I'll give you just a quick idea of what a matrix is, and we'll calculate the determinant. And so if your vectors aren't three-dimensional, then the cross product is meaningless. Basically, you have to have three dimensions to calculate the cross product. It really needs to be that third. So if you have two-dimensional vectors, just throw a 0 in the component that's missing, and then you have to make them 3D. If somebody's going to ask you about the cross product, it has to be that the vectors are three-dimensional. And we don't want to memorize that formula. We're going to talk about how we can use something called the determinant. Let's take a detour and talk about what a determinant is. Okay. So a determinant is a number that you calculate from a matrix. A matrix is just an array of numbers. Okay. Some rows and columns filled with numbers. That's what a matrix is. When your matrix is square, you can calculate this number that's called a determinant. A square matrix just has the same number of rows and columns. A matrix normally has square braces or parentheses around the array. So when you put straight lines around the array like this, you're announcing that you're about to calculate the determinant, and that determinant is simply just a number based on these entries in the matrix, and it'll be the entries along the forward-facing diagonal minus the entries along the backward-facing diagonal. Just a simple calculation. AD minus BC. Okay? And we're going to relate it back to the cross product in a second. So if you have the matrix 1, 2 going across and 3, 4 for the second row, what would be the determinant of that matrix? -2. 4 take away 6? -2. Great. How about -6, 2 and -9, 3? 0. Lots of places that make a mistake, but minus the -18 is a plus an 18, so they cancel out and you get 0. It's possible to have a 0 determinant. When you get to 240, we'll find out what that really means. It's very important when you have a 0 determinant. It says something about the matrix. Okay, and then here's just another one thrown in. When there's zeros involved, it makes calculating the determinant easier because you don't have to worry about some of the calculations, and so that has a determinant of +3. All right, great. So here's the deal. When we do cross products, it'll boil down to us calculating 3 of these 2x2 determinants. Okay, so it comes from a 3x3 determinant. So let's talk about how we calculate a 3x3 determinant. There's more than one way. I'll show you 2 ways. But the main way is what's called cofactor expansion. So I have these 3 rows and 3 columns. I have these 9 numbers. Okay. And if I want to calculate the determinant of a matrix that's 3x3, then I need to do the following. You really can do it about any row or any column, but in practice we use the first row. And for our cross product, we'll be expanding about the first row. I'm going to take each entry in the first row and multiply that entry by a 2x2 matrix. Okay? The way you get that 2x2 matrix is crossing out that row and that column. You really need to see it done. I mean, this is the recipe, but you really need to see it done. And then the explanation as to why this -1 comes in, really, I can't tell you until I develop a bunch of linear algebra, and that doesn't come until Math 240. But there's a -1 that needs to be factored in. Okay, so here's a number. Here's a matrix full of numbers. It's 3x3. And we're going to calculate the determinant of this matrix by expanding on the first row. Here's my first row here. I'm going to expand on that first row. According to what's above here, I take this first entry here, I cross out the row, I cross out the column, and I'll be left with this 2 by 2 matrix here. It's called a cofactor. So 1 times the determinant of that is part of my answer. When I move to the next entry, I do -3, okay? I cross out the row and the column, and I get a 2 by 2 matrix there, just pasting those two guys together. But I have to apply a negative to that. So maybe I should have done this in a different color. This is the negative that gets applied to that. This is my entry, just like I had a 1. Here's my entry, and then I have to, if I'm going to get the number correct, this -1 has to play a role. Why it's there, I can't tell you yet. But in 240, they'll do a good job, hopefully, of explaining why that's there. Okay, there's a whole matrix called a sign matrix where if you go expand about other rows or other columns, you have to associate negatives in certain entries. Finally, the last number here is a 2. So we cross out that row and that column, and we have that 2 by 2 matrix, and that's what gets multiplied by 2. So it's just a number. It's just a number we go and calculate. And so what do we get here? This is 9, take away 12. This is -1 plus a 20. And this is -3 plus a 45. That's what those 3 determinants are. Those guys get multiplied by the first one, a 1, the second one, a 3, and the third one, a 2. And we go and add these guys up. Okay, that's how we got a +3. So just get a number, whatever it is. Here it is, a -3, and if you triple 19, 57. And if you double 42, 84. So you get something. What is this?
138.
Thank you. All right. Now for us, when we get to vectors, we'll do these same mechanics, but in the end, our object won't be a number. In the end, our object will be a vector. And so we'll show how that comes up on the next slide. But this isn't the only way to calculate a 3 by 3 determinant. You might have seen a shortcut. And let me show you what that shortcut is on a different matrix. The shortcut to calculate a 3 by 3 matrix is to do the following. Raise your hand if you've seen this before. You write down the matrix and you copy down the first 2 columns. You ever seen that before? Okay, and then what you do is just a bunch of diagonals going forward minus a bunch of diagonals going backwards. You try to set it up like the 2 by 2 calculation is. It's a shortcut. It isn't, the official definition of a determinant uses the above method. This guy is just someone who discovered this and says, it gives you the same answer, which is true. And so there's a bunch of forward-facing diagonals. Multiply along there. There's a bunch of negative backwards-facing diagonals. Multiply along there. So I take and add these numbers together. So my first product is going to be a -2, a 72, and a 30 with a -30. I get those guys, add them up. Then I go backwards. These guys that are going backwards slashes, it's backward diagonals. I do the same thing there. I get a 36 and a 15 and an 8. And what I do with those two sums is I subtract them. The forward guys minus the backward guys, and I get a number. And so you can do your cross product. You can find your 3 by 3 determinant by doing that. And I don't care which method you use, whatever you're more comfortable with, do that. And there's even another way. So these are 2 ways. You choose whichever one you like. After a while, you get so fast at it that you end up in some kind of place where you're comfortable at. Okay. So when it comes time to find a 2 by 2, find a cross product, we make it's weird. This is very strange, this thing here. We have the first row. These guys are vectors, right? I is a vector, 1, 0, 0. J is a vector, and K is, so the first row is made up of vectors, but the second and third are the components of the vectors U and V. Weird. But it's just a tool, that's all, to help us get this vector in the end that's supposed to be orthogonal to both. Okay? What do? Cross out the row, cross out the column, take that entry times the 2 by 2 subdeterminant. Cross out the row, cross out the column, take that entry times the 2 by 2 subdeterminant, and then don't forget to apply the negative. Cross out the row, cross out the column, take that entry k times the 2 by 2 subdeterminant, and we have a vector because of the presence of i's, j's, and k's now. I have some number times I, some number times j, some number times k. It's the same as the formula that we had on the first slide. But we don't memorize that formula. We use this object to help us calculate it. Okay, let's do this for these two vectors will be done for today. I have the vector 1, minus 2, 1, and the vector 3, 1, minus 2. Okay, it's strange to write this, but it's true. We're going to make this and the order is going to matter. Whatever's first, before the cross product, that goes on row 2. Whatever's after the cross product symbol, that goes on row 3. The entry's there. And in the end, we get a vector out. Okay, we're going to have cross out i's, row, and column. We have negative 2, 1, 1, and negative 2. That's our I component. It's okay if I write it like that. And then our j component, cross out j's row, cross out j's column. We're going to have 1, 1, 3, and negative 2 determinant to find. But don't forget, negative 1 times that. And then finally, cross out k's row, cross out k's column. And so I'm using, instead of ijk notation, I'm using the brace notation, if that's okay. This guy was times I, and this guy was times j, and this guy was times k. I just didn't write it like that. Cross out that and get a 1, negative 2, and 3, and 1. So just what are these numbers? What's the first one? 3. Very good. Second one? Positive 5. Positive 7. Very good. All right, so I'll see you guys on Friday. We'll pick up from here. We'll talk about properties and applications of this cross product.